And welcome back to another Cosmic Journey. We're going to now wrap up our discussion around the moon by discussing the origin of the moon itself. So, what are our ideas for the origin of the moon? Well, most of the early hypotheses for the moon's origin followed one of three general ideas. The first was the fission theory, that the moon was once a part of the Earth, but somehow in the early history of the planet separated off. The next was the sister theory, that the moon formed together with, but independent of Earth, as we believe many of the moons of other planets formed. The next was the capture theory, that the moon formed elsewhere in the solar system and was eventually captured by Earth in its orbit. Well, the thing is, we can reject a lot of these theories for various reasons. First off, with the capture theory, its primary drawback is that no one knows of any way that early Earth could have captured such a large moon from elsewhere. I mean, the moon, for its size, and Earth, for its size, are much different than what we see in other celestial bodies in our solar system. One body approaching another cannot go into orbit around it without a substantial loss in energy. If we look at the fission theory, calculations show that this sort of spontaneous fission or splitting is impossible. There's not really a reason that all of a sudden it should just rip itself apart. Furthermore, it's difficult to understand how a moon made from terrestrial material in this way could have developed many of the distinctive chemical differences. Because remember, even though we have similar materials, they are not the same. And then when we look at the sinister theory, we say, well, this could be the most likely model, but a better explanation is needed to really kind of explain lunar material that's been separated from Earth. And so that leads us to kind of our current theory for the moon's formation, which is that of the giant impact hypothesis. To resolve the apparent contradictions, scientists developed a fourth hypothesis for the origin of the moon, one that involves a giant impact very early on in Earth's history. There's increasing evidence that large chunks of material, objects of essentially planetary mass, were orbiting in the interplanetary solar system at the time that the terrestrial planets formed. The giant impact hypothesis envisions Earth being struck by an object approximately 1/10 Earth's mass, or about the size of Mars. This is the largest impact Earth could experience without being shattered. So, we actually look at that impact. It would have disrupted much of Earth, injected a vast amount of material back into space, releasing almost enough energy to break the planet apart. Computer simulations indicate that material totaling several percent of Earth's mass could be ejected in such an impact. Most of the material would be from the stony mantles of Earth and the impacting body, not from their metal cores. This ejected rock vapor then cooled and formed a ring of material orbiting Earth. It was this ring that ultimately condensed into the moon. And of course, we also have some evidence of some of this probably within Earth's mantle as well, that some of this might have actually occurred. So this, of course, is our current best hypothesis. While we do not have any current way of showing that the giant impact hypothesis is the correct model, it could be wrong. We could have, a new hypothesis come along that's even better. It does offer us some potential solutions to most of the major problems raised by the chemistry of the moon. First, since the moon's raw material is derived from the mantles of the Earth and the projectile, the absence of metals is easily understood. Second, most of the volatile elements would have been lost during the high temperature phase following the impact. Because remember, the moon doesn't really have many of those volatile elements, which explains the lack of materials on the moon. Yet by also making the moon primarily of terrestrial mantle material, it's also possible to understand the similarities that we have, such as identical abundances of various oxygen isotopes.